Dear colleagues, good morning. We continue our session, and so the first talk, invited talk, will be by Andrej Čadež, The Puzzles of Crab Pulsators Phase History. How can the nebula participate in breaking the pulsar? Please.
Thank you very much. Well, this is the second talk that I'm giving on this topic. Last year I gave the kind of introduction. And the idea is that we have been monitoring the Crab pulsar optically with a very precise device, and we found out that the optical pulsations of the Crab pulsar follow perfectly the radio pulsation. Therefore, we conclude that the radio takes very good care of dispersion measure. And so that the pulsations, actually, also the radio pulsations measure the rotation of the pulsar without any interference with the dispersion measure between the pulsar and us. So, so this was the stimulation. Why we went and studied the history, the phase history of Crab pulsar again to see, because we saw that the phase history somehow. It has in the phase you can see some what people call the phasing noise, and it was thought before that the phasing noise was probably the effect of this changing dispersion measure between the pulsar and us, so that that's why the speed of light maybe changes a little bit to change the. But since the optical and radio show the same jitter in the noise, we thought that the radio actually gives us the right period of rotation of the pulsar, actually the right phase of the pulsar, so it's good to look what the phase is doing. So the first thing I wanted to show you is that here I present just the phases at the time. See the numbers, if you read, so from the year 1988 until now, the phase has made about 2.5 and 10 to the 11 turns. That's a huge number. But you see that the phase is perfectly straight line. It looks perfectly straight line. But if you fit a straight line to this phase, you get this. And you get still some 10 to the 7 excursion on the phase from the straight line. So, okay, then you do the quartic fit. And the quartic fit gives you still about plus minus 40,000 excursions. And then you do the fifths and so on, and then you do the breaking index law, because the Jotten Banks people say that the breaking index law 2.15 is perfect for the phase until, I think, 1988. But you can still see that you have about 1,200 turns going up and down the noise. So now let's play the same game, but we do. But we now fit not the phase, but the derivative of the phase. This is the frequency. So if you fit the frequency with the breaking index law, you get kind of excursions like this, and you see that you have parabolas. But now then you take the derivative of the frequency, and you can see that if you fit it with the breaking index law, you have sections which are straight lines. It kind of means that, okay, the breaking index law is a pretty good fit, but it is only good, in sections. So this is one section here, this is the other section, the third section, and so on. So actually, you can see from here that the pulsar phase, or the frequency derivative, consists of episodes which seem to be going pretty well according to a breaking index law, but the breaking index law changes from episode to episode. And the episodes actually are marked and are delimited by glitches, by huge glitches. You can see that the frequency derivative makes huge excursions during the glitch, but you don't know how much how much actually the phase changes during the glitch, you will see that the phase doesn't change very much during the glitch. The frequency derivative is huge, but the frequency derivative is very small. So if we go further, so the idea is now what you do, you say, okay, the phase obeys a breaking index law pretty well during episodes. And so what you do, you fit episodes by a breaking index law, but each episode to the breaking index law which best fits to the particular episode. So here you can see the history of the phase since 1988 until now, and it is now it's divided into episodes from 1 to 10. See, 1 to 10, and each episode is fitted with a breaking index law. Then the breaking index is marked here. You see, this breaking index goes here from 2 to 2.6. So this is 2.6, something like this, and the lowest breaking index is about 2.1. So this episode has a breaking index 2.6, this one is 2.5, and 2.5 something, and so on. But now if you fit this episode with the breaking index law, you can see that the residuals in phase are very, very, very small indeed. You see here and there it's very small, but then this residual goes down and kind of oscillates like this. And then this one, so in the whole time when the period has made about 10 to the 11 terms, more than 10 to the 11 terms, the residuals with respect to the breaking index law is only about 40 terms. In the whole period of... Now the funny thing is, now you can go on, you can ask yourself, well, that's funny. If you look at the episodes, the episodes always look very much like the same, because when the glitch starts, the phase makes kind of an oscillation. And so we tried to fit this residuals with the double sinusoids, damped double sinusoids. And you will see that if we do that, we get residuals with respect to the double sinusoid. Residuals are these things here, the small residuals here, but actually this line here is residuals of the data points with respect to the green and red lines, but magnified 10 times. So we can fit the whole phase history of crab from 1988 until now by first the breaking index law, but the breaking index law has in addition kind of double sinusoidal variations, and all this together gives you about 10 to the about hundreds over turn residuals, very, very small residuals indeed. Now here I just list the parameters of the breaking index law. You can see this is the time when the episode starts, the phase of this episode, and there are two parameters A and B, where I don't actually, there must be somewhere. Where did I have it? No? No? Sorry. Okay. Now these are residuals again. Now where yeah. This one does, yeah. Now I'm in trouble because I can't play my games. Yeah, okay. Yeah, these are, the fits for the residual double sinusoids, phi plus one damped sinusoid plus the other damped sinusoid. And these are residuals of residuals, and the error bars are 6 times the radio error bars. So the fit is not it doesn't fit exactly the radial according to their error bars, but if you take 6 times the error bars, then the fit is perfect. So there's still something left, but very little left with respect to the residuals. And now I can also, here you can see the parameters of the sinusoids, and it turns out that one sinusoid is, this is omega, lambda is a damping term of the sinusoid, and the second sinusoid has lambda 0, it seems to be undamped. I mean, but of course undamped because the time from which we determine the sinusoid is rather short with respect to the number of terms the sinusoid makes. Now, if you see this, then you're curious if what's going on. Are these things having some correlation? First thing I've showed you that the graph phase actually changes the breaking index during periods, and then you wonder if these changes of the breaking index have anything to do with something else. So the first thing that comes to your mind is the dispersion measure. So I tried. Here I plotted the breaking index as a function of time, but displaced by 1150 days, and the dispersion measure as given by Jodrbeck. And you can see there's a pretty good correlation. And here is the same thing. This is the breaking index. In fact, it's a breaking index. Unfortunately, I have missed the presentation. How is the breaking index law expressed in this? But this is S is n minus 2 times divided by n minus 1. This is n is the breaking index. So now this is another parameter S, which is related to breaking index, and the dispersion measure. You can see the correlation, and the correlation coefficient is about 7.4, which is pretty good, one would say. So the breaking index and the dispersion measure seem to be correlated, but with a delay of 1150 days, about 3 years. After 3 years, 3 years after the breaking index has changed, the dispersion measure has changed. So you go on. The other thing you might wonder is, you see, if you express the dispersion, the breaking index law in this form, nu dot is minus a certain coefficient, which is constant, times nu naught to the n, nu naught to the n, then you wonder what is this k, this coefficient. Now this coefficient may change during episodes, and here I plot the coefficient as a function, during episode. You see, the coefficient actually changes, and it changes in such a in such a way somehow that the power, the breaking power is about the same. When you change the breaking index, but the breaking power wants to stay pretty much the same. And what you see moving here, you can also say, okay, suppose I think that the whole period is describable by just one breaking index law, n, and if you change n, you see this is the number, the n. If you change n, you see that each episode actually fits very well with a certain n. See, the breaking index, if you fix n, then the k will change as a function of time. But then, of course, you don't have a breaking index law. But I just wanted to say that the breaking index law during one fixed constant during one episode is a pretty good approximation, because you can see when the blue line and the red line come together, they actually stay together on the episode. So, and here I plot again this k, dispersion measure as a function of time, and you can see some kind of a correlation. Another thing one might wonder is, you see, if you plot the frequency as a function of time here, and then you express frequency as a function of time just by the breaking index law, not with you forget about the residuals. Of course, then you get jumps between episodes. And what these jumps mean that the frequency can change. Why the frequency can change? Because the pulsar has obtained a torque impulse. So the pulsar has during the glitch received a torque impulse, and because of this it changes the angular velocity. But you can also see that the phi double dot, which means the acceleration, is different. Another jerk is different after the glitch than before. So you may wonder whether these velocity change and the acceleration change are related. And you find out, I mean, it's not necessary they will be related, but you find out, here I plot the velocity break and the acceleration break, and you can see that they are linearly related. That means that glitches are really sudden, and they are all the same in a sense. I mean, not the same in, you see, some glitches are very large, some are very small, but the change in the breaking torque and the change in velocity are linearly related, which somehow means that the mechanism of the glitch must be the same for every glitch. And now, okay, one thing you can ask yourself: what is the effective duration of the breaking impulse? And it's about 90 days, which is kind of consistent with the data, because it takes about 90 days for the glitch to not really to die, but you can see it's about three points here that the glitch is really wild, and then the glitch is kind of dies down. Now the next thing is, I have introduced the torque impulse before. Now if you look at the torque impulse and the amplitude in phase residual, so you see you have the torque impulse, which is proportional to this discontinuity in the acceleration, and you find out that, of course, that this torque impulse is proportional to the excursion of the phase after the glitch. This is the excursion of the phase after the glitch, which is delta n turns here. Delta n turns and the torque impulse are plotted here. And what you can see here, that they are again kind of linearly related, but there are two lines. And if you look at the graph here, you can see that there are two kinds of glitches. One kind of glitch is when the phase just goes down. But here you can see that the phase goes up. Residuals goes up. And here also residuals goes up and the residuals goes up. And the up and down residuals have two different branches. So this is just phenomenology, but I think it's kind of interesting. Now the other thing you might ask, what are the frequency of oscillations? I have just shown the graph of frequency of oscillations, but here I have tried to plot the frequency of those oscillations as a function of time. I said that there are two sinusoids are good to fit all this data here. But the first sinusoid has a much bigger amplitude than the other one. So actually, I tried with one, because it looks like one should be enough, but that's not enough. Somehow it doesn't work. But if you try it with two sinusoids, you can fit it very well. But the first frequency is the most important one, because it has the largest amplitude, and it's also the one that describes the damping. Now you can see that here the frequencies are plotted, the real and the imaginary part, so that this is the imaginary part and this is the real part of the frequency as a function of time here. And you can see that they do something. Then I wanted to see whether this frequency are related somehow to the breaking index. So I plotted the breaking index here and the frequencies, and you can see that, yeah, if you have, I mean, there seem to be, again, two branches. One branch where lambda is small and one branch where lambda is much larger. And you can see that this frequency here is about a half of this one, and this one is about twice this one. But there seems to be an order. But it's hard to say more than that, because now, how to understand the phase history? What I'm trying to say is that, you know, you can say that the phase, that a single breaking index law of this form describes the phase history of the crab, but this will require that k changes with time. And if you fix k, then you get your residuals with respect to such a breaking index law are really huge. But then the other point for looking at it is the one that I just described, that the crab actually is changing the breaking index log during the episode. Of course, also the k is specific for each episode, but this allows you to fit the phase curve of crab to a tenth of a hundredth of a turn for all the time. Now, the question is, what does the breaking index law mean? How do we understand the breaking index law? What produces the breaking index law? The first thing is, people were, you know, speaking about the breaking index law for many years, and the first idea was that the pulsars are breaking down because they're magnets and they rotate and they need dipole electromagnetic radiation. But you know, if you suppose it's just they emit some kind of multipoles, so that in this case the rotational the loss of rotational energy will be equal to the radiation of a multipole, which could be then expressed as the QL, which is the strength of the multipole, times omega to the 2L plus 1. Therefore, the breaking index is omega dot times omega over, sorry, this is omega double dot. The second dot is not seen here, I don't know why, but this is omega double dot times omega over omega dot square, is then this, but this number is of course always bigger than 1, but crab has a breaking index always smaller than 1, than 3. So electromagnetic wave emission into empty space cannot explain a breaking index less than 3. That's just, I mean, simple as that. But then I try just what happens if you assume that the pulsar is actually not emitting electromagnetic radiation into empty space, but there's a nebula around. And there's a nebula around, then this nebula is a kind of conducting plasma, and let's be as simple as we can, and let's say it's a homogeneous conducting plasma with a certain conductivity and certain epsilon, and then you can calculate what would be the equivalent of this formula here. What is the emission of a rotating magnet, and then you find it's kind of for a dipole it's similar than this formula here, you see, but you get mu naught over 6 pi omega, mu naught over 6 pi omega, but instead of omega over c2 cubed times pm square, you have this real k, where k is the wave vector, omega over c is the k vector times k plus imaginary and so on, where k of course is equal to epsilon times omega over c square plus I mu naught sigma, where it's the conductivity omega. And so you get, if KRD is much less than 1, RD is the radius of the pulsar, radius of the magnet, and of course it's much smaller than 1. Then you get this for the luminosity, and you can see that you have the omega 4 term, like here, but you also have omega squared term. So the breaking index law actually will depend on omega, and it will depend with, you know, on where omega lies with respect to sigma and RD, to this term here. So if you go on, now you calculate n, omega double dot omega over the square is equal then from the formula from the previous page. You get 3 minus this. So this makes the breaking index less than 3, and this is how much less. So now you can express the radiating power. You see, you can now, if this is n, you can solve then. You can solve sigma from n, and you replace L. You put n in the formula here, and you get the imaginary k. So you can express L as a function of omega to 4 like before, and then you had the breaking index down here, and you also get the imaginary k, which is mu naught sigma over c to this one. So if you do that, then you see you immediately get the size of the ionosphere if you have the breaking index. You don't know what's epsilon, but so if you assume that epsilon is epsilon initial times some epsilon, I don't know what's epsilon with this plasma, times n minus 1 to the 3/2. Because why do you do that? Because I know that the mechanism during glitches is such that it tries to make the L constant. L does not change. And then, so you get for the size of the ionospheres, you see the size of the ionosphere is about the radius of the sun, and sigma must be this very small number here. Okay? And if you look at the size of the ionosphere, you can ask yourself, you see, size of the ionosphere, according to this idea, this formula, will change with n. If n, you see, if n is larger, then the ionosphere would be larger. If n is smaller, the ionosphere would be smaller, and it changes by a factor of 3. It's about the size of this, you know, about the size of the sun, 3 times the size of the sun. I mean, but this is just a crazy idea, which let's see whether it can work at all. Now again, I simply copied the size of the ionosphere from previous page and sigma from the previous page, and then let's see what sigma would be. Sigma is electron density squared over me nu c, where nu c is the collision frequency. Now, if I take the classical formula, nu c is collision frequency is collision between electrons and ions. You put the formulas in and get this expression for sigma. Now, but we want to get this value for sigma. Now, if you plug in the numbers, you see you require this. For T is in Kelvin. So if, let's say, if T is 10,000 Kelvin, this is a huge number. So, you know, NE over NI would be, I don't know, 10 to the 10 or something absolutely ridiculous, completely unphysical. So this thing bugged me for very long. Why? It doesn't work at all. But then I remember, you see, collision frequency, the electrons are not colliding only with electrons and ions, but they are also colliding with gamma. And this gamma, are the virtual gamma, are of the gamma of the magnetic field surrounding the pulsar. Also the static part of the magnetic field. So if nu gamma is dominating, then if you know NE over nu gamma is less than 10 to the minus 4, then what can I say for the gamma nu gamma for the collision frequency with photons? Well, you know, you can get this expression here because this is the frequency in, but actually it's one of the time in which an electron that's moving synchrotron radiating in the magnetic field decays, and this is the classical expression for this one. And so you see this nu gamma can easily accommodate this formula. Now, I just want to show you, if I can, how I imagine, yeah. You see, just for fun, here I have plotted one thing. See, I have taken a magnetic field of a dipole and calculated orbits of electrons in the magnetic field of a dipole. Now, I have chosen one initial velocity, and all you see, the electron starts here, but it starts with the same velocity, but the velocity changes. It goes, you know, from here to here, like this. First, the velocity moves like this with respect to magnetic field, and then it moves like this. And you can see that if you start this way, the electron goes around. Oops. You see, the electron goes well here, and this points here show the direction into which finally the electron escapes. If the electron starts in the wrong direction, it will escape the field, because see, all these electrons have the same velocity and they keep the same velocity. So what I'm saying, what is nu gamma then? If these electrons escape from this position, they never come. But the blue ones, you know, just circle around. But how fast are they? What is the collision frequency? The collision frequency is actually the time it takes for the electron to come close, to make, you know, to come close to the field where it radiates strongly. When it radiates strongly, then it has changed all the parameters, so it has collided with photons. So now, what are glitches? They can be understood as sudden. Actually, if you look at Jodrell Bank data, they say that the really glitch part, I mean the part where the frequency changes very fast, only takes maybe a few days. Now, one thing that's interesting is, you see, now I have shown that there is a relation between the change in the braking torque and the change of the angular momentum of the pulsar during the glitch. And this change is related to certain energy, and this energy can be calculated, and it is about 10 to the 42 to 10 to the 43 ergs. Now, the funny thing is that see, these glitches, electrons seem to play an important role. If this is correct, I mean, if this has any sense at all, what I could just said to you, that the plasma around the pulsar is actually doing something, then electrons during glitch must be doing something really dramatic. Now, what can they be doing? Well, they will be synchrotron radiating. And it's an interesting thing to notice that actually the pulsar is actually not the nebula, has gamma ray flares. And I expect that these gamma ray flares are probably connected somehow to the emission of these electrons. We would not expect gamma ray flares to be exactly at the time of the glitch, because the gamma ray flares will be delayed because they have to, electrons have to travel somewhere else in the nebula to make a flare. But the thing is, this energy here, that's calculated for the glitch, is about 10 times the average gamma ray energy. So, but there are about 10 flares during an episode. The last one, not 10 power 5 flares or something like that. And somehow, this energy here is just about good enough to make the flare, all the flares observed. Now, the one thing to remember is this: the dispersion measure follows the breaking index with a 3 years delay. What does it mean? 3 years delay. Well, somehow I expect that during the glitch, the electrons are emitted from near the pulsar. Just because I said that this active ionosphere is just about the radius of the sun. But then these electrons are moving out. Probably 3 years away. But 3 years away is actually, it's a bit far, because the kind of the active nebula, the one that's emitting the line radiation, H alpha radiation, is about 1.5 light years away. The 3 years and the 1.5, I don't know what they're doing 1.5 years, but it's again something which I don't understand, but I find very curious. Now, I think I'm just not finished. And I just want to present a very curious, and my colleague said, a ridiculous analogy. Now, how do I imagine the pulsar breaking? Imagine a car, an electric car, which has a dynamo. This dynamo is here. You see, there's a dynamo. It's connected to the wheels. And the dynamo rotor is rotating, and this rotor has a certain inductance, and it has a certain intercoil capacitance, and then if you want to brake the car, you connect it to a resistor. Now suppose this car is just riding on a smooth road, and it is braking just because of wind resistance, and just for the sake of the argument, I suppose that it's proportional to velocity cube, although we don't know its own velocity. But then when I turn on the resistor here, close the circuit, then there's a certain current flows through through this resistor, which additionally brakes the car, and the induced voltage is the B times the velocity, and the current is Z2 minus 1, where Z the impedance, times U of t. Well, Z, of course, is an operator here because of the reactive elements. But in Fourier space, Z is this here. Now you can suppose you ask yourself, well, what happens when I put on the brake? When I put on the brake, then this coil and capacitor make an oscillation, but then this oscillation dies out, and when the oscillation dies out, omega is very small, and when omega is very small, then Z is just R, the resistance. So in this case, you see, I can divide now the velocity of the car into two parts. One is the part which would be described only by the resistance R, and the other part is delta V. This delta V happens only when I change the brake. Oops. So and delta E is mv dV is the dynamo excitation energy. Now what I do, now I just calculate the model how this car would move, and compare it with exactly with excuse me. Now I compare this model, so here I plot V. the function of time, and the real v. So this is, you see, this is the residuals. And if I go on, no, I'm so sorry. This is the. So you can see the residuals with respect to the breaking index law are just the same as for the pulsar. Now, I think that's about it, but I just want to ask one question: what to look for? Well, one thing what I would like, people to look for if you have an access to a telescope is how is crack changing. And so I went back to an old piece of data we had. We were observing crack spectroscopically for some years, but also with trying to detect the phase. So I got some data which we got in Cananea in 2002 and 2004. And in 2002 we took spectra with a lower resolution and a wider slit, and in the 2004 with a higher resolution and a smaller slit. So they are not quite comparable. But so I went with the Photoshop, I tried to make them equal size. And you can see that when this picture changes, it changes from the spectrum of along the same slit in 2002 and 2004. 2002 is the one that's kind of blurry, and 2004 is the blurry image. And you can see this is the slit along. It's along 0 degrees, you could say. It's kind of horizontal. And you can see that, I mean, this slit looks pretty much the same in the 2 years. And now if you go on, this one doesn't. You see, it does look the same, but not really, because you see this one here, it was, this part here was very weak before, but now it is strong. So again, unfortunately, this is not a completed work, but I must warn you, it's possible that the orientation of the slit was not exactly the same. But so I tried many slits, and somehow in some cases I see quite consistent. In some cases I see differences. So it's hard to say, because I don't have pictures of the position of the slit, unfortunately, on the sky. But it appears to me that in some direction, there was some direction the line radiation has changed a lot. And this is something that is worth looking at crab. And that's, thank you very much.
Thank you very much for your questions. Okay, then my first question. So it is very nice that you have shown these breaking lines, but possibly, okay, so you got this, but maybe there may be not completely lines, but parabolas with a very small curvature. Okay, if you will show, so when you have these broken lines for the phase, so you you argue that the phase derivative is constant, but it looks, maybe this is the curvature of the screen, that it is small, but there is some curvature of these lines, of these parts of lines. No? You have not checked this?
No, I don't.
No, so I just suggest that there is some observational material for next order theories. So very interesting results. But as for me, as while interpreting variable stars, so we look for these things, and so this result seems to be very interesting and promising for maybe next studies. Maybe. Okay. Other questions, please. No questions. Okay. And thank you very much.